All right, so this unit is all about circular motion, right? Whenever you have an object moving in a circular path like that, we say it's in circular motion, right? As the name implies. Now, we're not just talking about generic circular motion. In this class, we have a very specific type of circular motion that we discuss, and that is uniform circular motion. Uniform circular motion. Now, uniform circular motion is specific in that objects move in a circle at constant velocity. Okay? And that's kind of the important part right there. That constant velocity is what makes it uniform circular motion. When you start having objects moving in circles and they're speeding up and slowing down, things get complicated quickly. So in this class, we stick with mostly just uniform circular motion like this. Okay? So when we're looking at an object moving in circular motion, like this one over here, our velocity vector, that constant velocity that we see in that uniform motion, is always going to point tangent to the circle. This is our velocity vector right there. It's always going to point tangent to the circle. Meanwhile, the acceleration that the object is experiencing is always going to point into the circle. Why is that? Well, if our velocity is tangent to the circle like this, in order to keep our object moving in a circle, our acceleration has to point to the left. Because all that acceleration is doing is it's just pulling that velocity to the left, keeping it in that circle. Now that acceleration has to be a really specific amount so that it doesn't increase or decrease the velocity and is just enough to pull it into the circle, keep it in that circular motion. Okay? Now, similarly, because that acceleration is pointing into the circle, because of Newton's second law, which says that net force equals mass times acceleration, if there's an acceleration pointing that way, that means that the force acting on the object has to also be pointing that way. All right? Now, this force and this acceleration, they have special names that we give them when the object is moving in a circle. Let me open up some space over here to write down some definitions for these special forces and accelerations. This force, we call it the centripetal force. All right? And the centripetal force is going to be any net force which causes an object to move in a circle. Okay, so this force up here, that is our centripetal force. We're going to label it capital F subscript C. All right? Now, it's important to note, centripetal force is not like one specific force. You know, we have this list of forces like force of gravity, force of tension. Centripetal force isn't on that list. It's a label we give to one of those forces on our list, right? So I'm going to write down here, it's a label, and I'm going to underline that. That's important. There is no one centripetal force. Let's say in the case of that lab that you guys did where you were swinging the rubber stopper on that string, force of tension was our centripetal force in that case. Or when a car takes a turn around a circular curve, the centripetal force in that case is going to be friction. That is what is keeping the object in the circle. Okay, so we have this centripetal force which we can label to specific forces causing objects to move in circles, and then the acceleration that goes along with that, we call it centripetal acceleration. Basically has the same definition, but rather than saying any net force, we say an acceleration which causes an object to move in a circle. Just like centripetal force, we label it acceleration subscript C for centripetal acceleration. All right? So there you go, kind of the basics behind our centripetal force keeping an object moving in a circle. Other important thing to note, centripetal in this case, it actually means center pointing. So your centripetal force, your centripetal acceleration, they're always going to point towards the center of the circle, no matter where the object is. Let's say it's over here. Well, then our centripetal force and acceleration will point towards the center of the circle again. All right? Okay. Next thing we're going to talk about is centrifugal force. All right? Centrifugal force is kind of confusing. It's probably something you've heard of before, but maybe not really understood exactly what it is. I think the best example to think of when thinking of centrifugal force is when you're driving in a car and you take a sharp left turn. If your car, there's our car, takes a sharp left turn, well, when you're in it, it doesn't actually feel like you're moving to the left. In fact, you probably feel like you're being pushed this way, right? You're being pushed to the right. This is centrifugal force. It is an outward facing force, outward facing force that you feel like you experience when you are in circular motion. Now, I'm here to tell you that this is made up. It is an illusion. It doesn't actually exist. What you're really experiencing is the fact that when you're driving in your car like this, your velocity vector is pointing forward, right? That's your velocity vector. But you take a sharp left turn. Well, if we think back to Newton's first law, an object in motion stays in motion, and you're not going to want to change that motion. Your body is going to want to keep moving forward like this. But the car has already started turning left. So what it's going to feel like to you is it's going to feel like you're being pushed that way, when in reality, you're simply continuing forward while your car turns left. Relative to the car, it feels like you're moving to the right. But there's no actual force pushing you to the right. That centrifugal force that you feel like you might be experiencing doesn't actually exist. All right? All right. Let's start talking math now. In the lab we did, in a perfect world, when we graphed our centripetal force versus velocity, it should have looked something like that. I know a lot of us didn't get those exact results, but that's what it theoretically should have looked like. Now, if that's true, then that means that somehow our centripetal force is going to be equal to or proportional to velocity squared. All right? Then, if we look at some of our other data, we look at that linearized data for this graph. If we kind of squint real hard, maybe cross our fingers, you can see that actually, as we increase radius, the slope of this graph decreases. And additionally, we're going to multiply mass by this. And this is our centripetal force equation. Okay? So whenever you have an object that is experiencing a centripetal force, you can solve for the amount of centripetal force by using this equation here. Now on your equation sheet, it's not actually going to show up like this. Unfortunately, all that's on our equation sheet is the equation for centripetal acceleration. Okay? Now if we use Newton's second law, net force equals ma, and we take that centripetal acceleration and plug it in for our acceleration up here, we'll end up with our centripetal force equation. So that's what you got to do on your own. You got to remember that if we are dealing with an object moving in a circle, we got to take this new acceleration and plug it in up there to solve for it. All right? A couple other helpful equations here are going to be our equation for velocity for an object moving in a circle like this. It's going to be 2 pi r divided by the time it takes for it to make one full rotation. That's going to be our period. Capital T represents period, and that is the time it takes for one rotation. Time for one rotation. Okay? Now, sometimes the AP likes to throw a wrench in the system, and rather than talking about period, it likes to talk about something called frequency. Frequency is the inverse of period. It's the opposite of period. So what is it? It's the number of rotations in 1 second. All right. Now there's an equation that connects these two. Like I said, it's the inverse, so period equals 1 over frequency. This kind of weird looking fancy F represents frequency here. All right? Doesn't come up a whole lot, but it's important to know because, like I said, the AP likes to mess with you guys. All right? Okay, let's do a couple quick examples here. So let's imagine we have an object moving in circular motion. And let's say it's got a velocity of 3 meters per second. And it's experiencing, somehow we've calculated or measured that it's experiencing 1.5 meters per second squared worth of its centripetal acceleration. All right? Now, we're trying to figure out what is the radius at which this object is moving. Okay? What are we going to do? We're going to use our centripetal acceleration equation because it's got v squared in it and r, right? We got centripetal acceleration, we know that, that's 1.5. We got velocity, that's going to be 3 squared, and we got radius, that's what we're trying to solve for. Multiply r over to this side, 1.5r equals 9. Divide both sides by 1.5, we get 6. Okay, 6 meters to be specific. Got to put in your units. So, the interesting thing about uniform circular motion is that in order to achieve it, it needs to have very specific values, right? This case here is the only case in which this object would actually move in circular motion. It needs to have a radius of 6 meters. It needs to have an acceleration of 1.5 meters per second squared. It needs to have a velocity of 3 meters per second squared. If we change any of those things, the circular motion breaks down, essentially. If our velocity increased, like let's say this object was experiencing 1.5 meters per second squared of acceleration still had a radius of 6 meters per second, but instead had a velocity of 5 meters per second, maybe. Well, if this were a larger velocity, then this object, the acceleration wouldn't be strong enough to keep it in that circular motion, that uniform circular motion, so it'd end up moving out like that. Something like that. Or what if the velocity was the same, but the centripetal acceleration was less? Well, if it had less centripetal acceleration, then it wouldn't be strong enough to keep our object moving in a circle still, so again, it would fly off like that. On the inverse, if our centripetal acceleration were doubled, let's say it's 3 meters per second squared, but our object still has the same velocity and radius, well, that acceleration is going to be too strong. It's going to pull the object, it's going to pull its velocity so hard that it's going to break out of the circular motion and move towards the center of the circle rather than maintaining its circular motion, that perfectly uniform circular motion. All right, so these scenarios require those specific numbers in order to work at all. Okay? Okay, let's hit up one more example before we end this video. Let's imagine that we have an object that is moving in a circle, but this time, rather than a horizontal circle, maybe around somebody's head, it's a vertical circle. So it is being swung in a circle in front of somebody. So this would be up and down here, okay? Now, let's say that it has some velocity v. We don't quite know what it is yet. The mass of the ball is 0.15 kilograms, and the radius of this string, or the length of the string, is 1.1 meters. Okay? So, for our first objective, we're going to determine the minimum velocity required to keep it in a circle. Required to keep object in a circle. Okay, so here's what we got to think about. I'm going to think about the free body diagram for this object. up here in this very moment where it's at the very top of its swing, our free body diagram looks like this. We have force of gravity pulling down and force of tension pulling down as well. Okay, so let's think about the centripetal force then. In this case, remember that centripetal force is going to be the net force causing the object to move in a circle. Or it is all of the forces that are pointing towards the center of the circle. In this case, it's both of these. In this case, force of gravity and force of tension combine to become the centripetal force of this ball at the top of the circle, right? Okay, that's helpful information because we're trying to figure out the minimum velocity required to keep it in the circle. Well, if we want the minimum velocity required, then we want the minimum amount of centripetal force because those two things are directly related. So how can we apply the smallest amount of centripetal force to this object? Well, we can't change force of gravity. That's always going to be applying to our object. What we can change is the force of tension, how hard we're pulling on that string. So what would the minimum amount of centripetal force be? Well, it would be when tension is 0. If we got rid of all the tension in that string, that would be the minimum amount of force that we can apply to this object to keep it in the circle, which is going to tell us the minimum amount of velocity required to keep it in a circle. Okay? Okay, so let's get rid of that tension. It's going to be 0 in this case. And here we are. We actually know an equation for centripetal force and an equation for force of gravity, right? So centripetal force is going to be mv squared over r, and force of gravity is going to be m times g. M cancels out. We can multiply r to the right side. We can take the square root, and we can find that to solve for that minimum velocity, it's just the square root of r times g. We plug in our numbers. We get, 1.1 times 9.8. Take the square root of that. Our answer comes out to 3.28 meters per second. Okay, that's the minimum velocity required. Okay, now let's talk about the second part of this question. For the second part, we're going to consider what's going on with this ball at the bottom of the swing. All right, let me open up some space here. All right, so here we go. Part B asks us to find the tension in the string, find the tension at bottom of circle. Okay, so we're going to consider what's going on with this ball at the bottom of its circular motion rather than the top. Now, one important thing to note is that at this point, we're going to say that velocity is going to stay the same. For this scenario, we're going to say it's going to be the same thing as last time. Okay, let's draw the free body diagram for the ball at the bottom of the circle. It's going to be pretty similar, but a little different, because in this case, gravity is still pointing down, right? Fg is still going to point down, but in this case, tension, the string is going to be pointing up, so tension points up. All right, so we're trying to solve for tension. We're going to use centripetal force again and consider the fact that centripetal force is the net force causing the object to move in a circle. Well, then we would have a positive force of tension minus force of gravity, because force of gravity is essentially trying to pull the object out of the circle, while force of tension is trying to keep it in the circle. So we're trying to figure out how much tension does there have to be in order to keep our object in that circle. All right, so let's go about solving this. We have centripetal force is mv squared over r equals force of tension we're trying to solve for minus mass times gravity. Okay, so then if we rearrange things a little bit here, we're going to find that force of tension is equal to force of gravity plus that total centripetal force. Okay, so let's plug in our values here and see what we get. We have a mass of 1.1 times 9.8 plus our mass of 1.1 times our velocity of 3.28 over our radius. Oh, sorry. Oops. Mass isn't 1.1, it's 0.15. 0.15 divided by our radius here. That is 1.1. Okay? Okay, so we plug this into our calculator. We solve for it. Solve for force of tension. We should get an answer of force of tension equals 7.35 newtons. And that is going to be the force of tension in the string. That is what is going to keep our object moving in this circular motion. Okay, so hopefully this video is helpful. I'm going to make a video tomorrow with some more examples, some more complicated examples, but hopefully this helps clear up any confusion from notes today. All right, see you guys later.